to that. If you look at some of his career, knowing me for a bit of time, I was vice chair of the CWH Sri Lanka chapter, and also I think on last CWH World Conference also there was that presentation you did, presentation post presentation you did was well received. So it was their work. Other unique thing is I don't know whether any other architects, if there are architects, not usual job they can do, but going and doing the design buildings, all that. But what is unique, I have observed with architect Nirodha is that this parametric design side, where his mathematics is really good, like it's great. We just talk about engineers and mathematics knowledge. His mathematics knowledge, if you take the opportunity to talk to him as well, what he has done, bringing all that together and linking to the parametric designs, all that mathematical background to the architecture. So I don't think I have not seen anyone, even in Australia, doing that, architects doing that. So welcome. I can go on and on rather than taking time. I will go there.
Good morning, sorry for that purpose. Anyway, folks, thank you very much for that wonderful explanation about me. Okay, so let's begin. Right, so I was invited here because we designed tall buildings. And these are some of the tall buildings we have designed for the last 5 to 10 years. And some of you have worked with me on this premises, of course. The news is we no longer design buildings like this. That is because the design technology I was seeing has been radically changed for the last 3 or 4 years' time. Okay, so I'm going to explain the modern design technology of tall buildings. It's all about design. I'll try to explain it in a simple way so at least some of you will understand some part of it. Okay. Right, so it's about design. This is a design. So what kind of a design is this? This is the greatest design in the universe. So if you look at this design, it has a sensory system down there. It has a power supply system. It has a mobility system. And also it has a reproductive system. So if you take this design and put it on a wall and wait for, let's say, million years, it takes the form out of that context and evolves and it becomes something like this. If you take this and put it in water and wait for another 100 million years, it becomes something like this. So it changes the form and takes form out of context and become different things. It's the same design. So if you put it in ground, this is what happens to it. You can see the same features are there. You have the sensory system down there, you have the power system, you have the mobility system, everything is the same. And this is what happens when you put it in the sky. So you can see there are no different designs for water, different designs for land and so forth. It's one single design. So it goes according to the context. I hope it's because this is how we design our buildings today. So we change parameters and change proportions and it becomes different things. So that is how the tall buildings are designed today. So if you look at this building we have designed, it's not any further rigid one single design. So things can move and adjust. So we get, for this example, I have taken the height of the building. So as you adjust the height, it's not just a graphical adjustment. You can see, for example, when you increase the height of the building, the requirement of the lobby space at the ground increases automatically. So you need more lobby space. So you can see as the height of the building increases how the ground floor lobbies are getting there. And it is very dynamic. So this particular building, its form is not just varying in the wind, so you can see. If you look at these windows, for example, you can see as the width of the building increases, you need more light and ventilation. So the windows appear and then they disappear. So it is as the context of the building change, the proportions change and parameters change. For example, now this one is how this particular design reacts to different climates. So as the climate is a colder climate, you need not to have windows, it is just glass panes. And when it comes to tropical climate, what happens is we need overhangs to shape the building and we need dry overhangs. So this is how this building reacts to different climate. As the climate changes as a parameter, this is how the building reacts. So it is all about working with context. Climate is part of the context. So when I say context, climate is part. The form of the land is a part of the context. So as the form changes, as you change the form of the site to a linear one, the form of the design changes. Land value is a parameter like that. The budget of the climate is also a parameter like that. So when these things change, the building change, it adapts. So that is how we design our buildings. So as the context changes, the building changes, like that feature changes. So you will wonder how to create such design. So that is my topic. So that is what I am going to explain today. I'll try to explain in a simple manner how to do that. So it is all about, as I said, I think Mr. Kandy also explained something similar. It is all about understanding relationships, how things are related to each other, and modeling these relationships. To explain this, I will bring you a very simple example. Buildings are complicated. We will forget buildings. I'll explain in another simple manner. This is the sun. Its mass is 10. And this is a satellite. Its position and velocity is given, it's fixed there. We can't change it. And this is the trajectory of the satellite. So our task is to play with M, not any other thing. We can change the mass of the sun and then play with the trajectory of the satellite, how it moves and changes as the mass changes. So how to do this? The first thing is, when we are designing this trajectory, is we set up the playground to play with this. So what we do is, we first identify the things that are predominantly going to govern the form of this trajectory. So I think all of you know, there are only basically two things. One is the Newton's law of motion, F equals mv. The second one is the Newton's law of gravity. So simple M is the mass of the satellite, capital M is the mass of the sun, and R is the distance between them. So there are many other things that will govern this. For example, the sun emits a high level of electromagnetic radiation, so although it doesn't have mass, it has momentum, so it pushes the satellite out. So I'm the one who's designing this now, so I forget that. I can't work with that. Relativistic things will work out if the satellite moves very fast, so it is so far from the sun. We have to consider time variant distance, so we are not going to do that. I'm going to forget that. So if the mass of the sun is small comparison to the satellite, this will rotate from a center point like that, so it will be complicated. So I consider the mass of the sun is very high and it is fixed and nailed on the space, it is not moving. So that is how I design. So now I have taken it into me and I am the one who is designing this. So if F equals mv, if that m is the mass of the satellite, so this is the force on that and this is the force on the sun. So we will compare that. Mass of the satellite disappear and then this simple equation governs everything. It's a very simple one. Acceleration of the satellite is the mass of the sun divided by the distance. So this sufficiently explains what it is, and we can play with this. So designing this trajectory of the satellite is all about designing and modeling this relationship. So how to model this relationship? One way is you can just take a piece of paper, you can calculate it, and then take. The second way is you can feed this relationship into a computer, probably as a vector field. It's a divergent vector field. And after you do that, you can play with M and then see what happens with this trajectory. So that is all what we do as designer. So when the M change, the trajectory change. So different conditions of gravity give different trajectories. So when the gravity is very high, it will spiral into the sun like that. If the gravity is not so high, it will be a circle. If the gravity is weak, it will be a ellipse. And as the gravity goes down, it will be a parabola kind of a thing. So different conditions of gravity changes. It's very much analogous to what happens to this design also when gravity changes. So when the gravity is very high, this is an elephant. It has very large legs. So as the gravity goes down, let's say in a low gravity condition, it is the same as this will be an elephant. In a very low gravity condition, an elephant would look like this. If we suddenly increase gravity, this elephant will not be able to get up with this flimsy tiny legs. It is same with the buildings as well. So this is a building we have designed to experiment this gravity thing. So its building reacts to gravity. So when the gravity is slow, the form of the building is like this. As the gravity goes down, increases, it changes, and with high gravity, it becomes something like that. It's a single design that operates when we change gravity. So buildings, only thing is buildings are little complicated than that. Gravity is not the only thing that governs the form of the building. So there are many things. So as I explained, land value is one parameter. The climate is another parameter, the form of the land is a parameter, budget of the client is a parameter, and there are many other parameters. So relations are complicated. So if I go into write an equation connecting all these things, it will be a very complicated equation, and we can't work with this. So what do we do when we can't work with equations? It is complicated. We draw diagrams. So that's what we learned from Richard Feynman. So when the quantum dynamics was so complicated, he came up with this brilliant idea of it is called Feynman diagrams. To draw a diagram to explain all these equations. And as Dr. Davis explains, that is how neural network people also work. So they represent an equation as a circle. The circle has inputs. There can be many inputs, and there is output. So this is the kind of approach we use in designing our buildings today. We are working with visual programming languages. So each of these boxes is a mathematical operation. We can put in several things into that. We can put in vectors, we can put in fields, we can put in scalars, and we can put in matrices and also geometries. We put them in, and the operation will happen, and it gives an output. We connect it to another operator. So likewise, it's a matter of building up this network, and that is the design actually. So this is how we design. What we don't do is we take someone else's model, we feed up the numbers and we see what it is. For each building, we design its genotype based on scalars, vectors, and fields. So that is how we design buildings today. So what we have learned is the form of the building is an outcome of a complicated number of parameters. It's not a simple thing. And unless you set up the playground to play with these parameters, we are not going to get the form of the building right. So that's it. Thank you.
I think we are running out of time, so we can't ask questions.
You want to listen for our next time from both of you.
Thank you very much for this.
Yeah, thank you,